In the second example, we are going to try to approach the problem from the opposite angle. So this is going to be a design example. So the previous example was an analysis example where you were given the sizes and given the currents. You were asked to calculate what the parameters of the op-amp were. In this case, we are going to pose the inverse problem, which is actually a tougher problem. So we are going to list out the specifications of the op-amp, and we are going to be asked to derive the sizes of the devices as well as the bias currents. So we will use the same parameters that we had used before. Mu n Cox is 100 microamp per volt squared. Mu p Cox is 50 microamp per volt squared. The threshold voltages Vtn and Vtp are both 1 volt. The power supply is 5 volts. The minimum length is 0.5 micrometers, and lambda n and lambda p for this minimum length is 0.02 volt inverse. So these are the device parameters. So let us now list out the specifications. So these are the desired specifications of the op-amp. So let us say that you need a DC gain of at least 100, and the unity gain frequency omega u should be equal to 10 megaradians per second. The slew rate of the op-amp should be 1 volt per microsecond. The input common mode range should be between 1 volt to 3.5 volts, and the output swing should be 3 volts peak to peak. So these are the minimum required. So if the DC gain is more than 100, that is fine. So you need a minimum DC gain of 100. You need a minimum omega u of 10 megaradian per second. You need a minimum slew rate of 1 volt per microsecond. These are the required minimum input common mode range. The common mode range can be wider if required. And finally, the output swing, minimum swing required is 3 volt peak to peak. Now, our job now is to translate these specifications into a set of widths and lengths and bias currents for the transistors. So now let us start off listing out the requirements. So first of all, each of these parameters, specifications that you have required, actually depends on certain variables such as GM, GDS, capacitance, etc. So the one thing we need to we have not added is the load capacitance CL, which we shall say is 10 picofarad. So now you can see that you have several sets of parameters. Now it is very difficult to set up equations in n equations in so many variables, because very often there is no one unique solution. The number of constraints listed here are actually smaller than the number of degrees of freedom, so there are actually many solutions. So we will try to approach it in a somewhat of a logical manner, where we can try to set some of the parameters first. So the first thing to do is do not set up n equations in n variables and solve it, right? That is not the way to go around, because you have several parameters such as gain, omega u, slew rate, etc. And it turns out that there may actually be no one unique solution, so we need to be a little bit careful. And finally, please note that in this particular case, there are other specifications that I have not given, such as noise, offset, or power consumption. So let us try to approach this in a different manner. So first we'll write down the dependence of each of these parameters. Now it is logical for us to start with the parameters that depend only on one variable. So let us look at which those parameters are. So clearly those two parameters are omega u and the slew rate. So let us start from there. So omega u is nothing but GM1 over CL, where GM1 stands for the transconductance of the input pair. So this should be equal to 10 megaradians per second. This means that GM1 should be equal to 10 into 10 power 6 times 10 into 10 power minus 12 or 100 microsiemens. So this now is a good place to start, because this lets us set the value of the GM of the input pair, which is one of the most important parameters in your design. Now let us look at the slew rate specification. So the slew rate specification depends only on the total bias current, which I'll denote by 2I0 over CL, and this is supposed to be 1 volt per microsecond. So which means 2I0 is 10 power 6 times 10 into 10 power minus 12 or 10 microamperes. This means that each transistor input pair has a 5 microamp bias current. Now it turns out that all of the other parameters depend on many other variables, but let us look at them one by one. The DC gain, so this is one. Number two, the third parameter we'll look at is the DC gain, and the DC gain is supposed to be 100. This is nothing but GM of the input pair over the sum of the GDS2s at the GDSS of the output pair. Since we have already found out GM1 here, we will plug that in here. So this is 100 microsiemens over GDS2 plus GDS4. And now this tells us that GDS2 plus GDS4 should be equal to 1 microsiemen. Now we will now make a judgment call, and this is one of the parts of design, is to instead of setting up equations in variables, we will now make a judgment call and say let the two resistances or two conductances be equal. Let GDS2 be equal to GDS4 be equal to 0.5 microsiemens. So please note that this is the minimum GDS2 required. If GDS2 were smaller than this, then the DC gain would be larger. The important condition is that the sum of the GDS2 should be larger than 1 microsiemen. Now let us look at the input common mode range spec. The input common mode range says that the input common mode should be variable between 1 volt and 3.5 volts. What does this tell us? If please remember that for a for the one stage op amp we have seen so far, the minimum input common mode is equal to VD sat of M0, which is the current source, plus VGS of the input transistor. Now clearly the threshold voltage of the device is already 1 volt. We now have a problem because VGS1 should already be larger than 1 volt. VGM in has to be larger than 1 volt for the op amp that we have seen so far. M0, M1, M2, M3 and M4. Now clearly for the op amp we have seen so far, the minimum input common mode is the point where M0 goes to the edge of triode region, where this is VD sat, and you need a minimum VGS1 across the gate source of M1. Now clearly a minimum input common mode level of 1 volt is not possible for this op amp. So however, please note that this is not the only one stage op amp possible. As we have seen, the NMOS device and the PMOS device have identical small signal pictures, which means you should be able to interchange the NMOS and PMOS transistors and be able to get a circuit with the exact same small signal characteristics. The only difference being that the bias points would be different. So let us now look at the PMOS one stage op amp. So far we have been looking at the NMOS one stage op amp. Clearly that will not work in this particular design example. So let us build the PMOS one stage op amp. So in the case of the NMOS op amp, you had a transistor M0 that acted as the current source. So now you need a PMOS transistor M0 that would act as a current source, pumping current of 2I0 into the differential pair. Now this particular circuit will also have a PMOS input pair, and let us say this is the positive input and this is the negative input, and now the PMOS current mirror here would be replaced with an NMOS current mirror. And now these transistors are M1, M2, M3 and M4. The sources of the NMOS current mirror is connected to ground, analogous to the connection to VDD for M3 and M4. Now it turns out that all the equations we have written are valid for this particular op-amp also, since we have not gone from the small signal parameters GM and GDS to the bias points ID and mu Cox, etc. So now let us look at the minimum input common mode range of this particular op-amp. So we are now going to look at the PMos op-amp. So for the PMos op-amp, all the equations are valid, but we are specifically interested in the input common mode. So if I were to start reducing the input common mode, I can see that this particular voltage is constant because there is a current of I0 through each of these pairs of devices, M1 and M2 and M3 and M4. And the output, of course, is taken at the drain of M4. And you can see that this node has a constant voltage of VGS3. And the gate of M1 can go lower than this node by a value, by a voltage equal to the threshold voltage of the PMOS transistor. Which is VT1 or VTP. Now clearly this can be less than 1 volt if required by choosing VGS3 appropriately. Now it is clear that the PMOS op-amp is the circuit that we need to use in this case. So now let us continue with the PMOS version of the circuit. So now for this circuit we now know that 2I0 is equal to 10 microamps, and therefore each transistor has a bias current of 5 microamps. Now based on this we can now calculate the W over L, etc. So let us now come back from the expression for GDS2 and GDS4, because the minute you know the bias current you can calculate the value of the length of the device. So as you can see, GDS2 is equal to GDS4 is equal to 0.5 microsiemens. Now we are given that the lambda for L-min of 0.5 micron is 0.02 volt inverse. So let us assume that L is equal to L-min and find out what the value of GDS2 and GDS4 is. So for our circuit, if we were to use L-min, GDS2 is lambda P times I naught. This is 0.02 times I naught is 5 microamps or 0.1 microsiemens. Similarly, GDS4 is lambda n I naught, which is again 0.02 into 5 microamp, which is 0.1 microsiemens. It is clear that in this particular case, an L min already gives you a larger value of RDS2 and a smaller value of GDS2 and GDS4 than is required. So clearly, GDS2 of 0.1 microsiemen and GDS4 of 0.1 microsiemen is more than enough. With these values, we decide that L1 is equal to L2 is equal to L3 is equal to L4 equals 0.5 micrometers. If the value of output resistance was not large enough, if GDS2 and GDS4 were not small enough, you would have to increase the length of the transistors to get a larger output resistance. In this particular example, this is good enough. Now, you can see that the DC gain is now larger than expected. DC gain is GM1 by GDS2 plus GDS4. As we have seen earlier, the value of GM1 was determined to be 100 microsiemens. So therefore, the DC gain is 100 microsiemen over 0.1 microsiemen plus 0.1 microsiemen, which is 500 volts per volt. We wanted a minimum gain of 100, but we now have a larger DC gain than required, which is always better. So the DC gain spec is met. Now the next thing to do is to calculate the width to length ratio of M1 and M2. Now GM1 is nothing but root of 2 mu C aux to 2 mu P C aux W over L of 1 times I naught. This is nothing but root of 15 to 10 power minus 6 over L of 1 times 6. Therefore, you can see, since GM1 is 100 microsiemen, GM1 squared is 10 power minus 8. This is equal to 5 into 10 power minus 10 into W over L of 1. This means that the width to length ratio of transistor 1 is 20, or so this means M1 and M2 have dimensions of 10 over 0.5. So 10 micron over 0.5 micron. So now we now have the sizes of M1 and M2. Let us now decide the size of M0. Since we know the size of M2, we can now calculate the value of the size of M0 in the following way. So we know that VCM in max should be equal to 3.5 volts. We know that VSG, this should be equal to VCM in max is equal to VDD minus VSD sat 0 minus VSG 2, because the maximum input common mode happens when you have exactly VSD sat across M0, and therefore the common mode at the input will be exactly VDD minus VSD sat 0 minus VSG of 1. Now VSG1 is given by the following relationship. It should be VT plus, so let us calculate it in a different way this time. So let us calculate it from the GM. GM1 is 2ID1 over SG1 minus VT, VT1. So let us calculate it from this expression. This means that VSG1 minus VT1 is 2ID1 over GM1. So VSG1 is VT1 plus 2ID1 over GM1. VT1 is 1 volt plus the current through M1 is 5 microamperes and GM1 is 100 microsiemens, and therefore this is nothing but 10 microamp over 100 microsiemen. This is 1.1 volts. In such a case, the value of VCM in max, which is 3.5 volts, so let us write that down here again, is VDD minus VSD sat 0 minus VSG1. So 3.5 volts is 5 volts minus VSD sat 0 minus 1.1 volt. This tells us that VSD sat 0 has to be equal to 0.4 volts. Now, since we know the current through M0, we can now calculate the width to length ratio of M0 itself. So VSD sat 0, so 0.4 volts is equal to 2ID0 over mu P C aux W over L of 0. .16 into 50 into 10 power minus 6 into W over L of 0 is equal to 2 into 10 into 10 power minus 6, because the current through M0 is 10 microamps. So 8 times W over L of 0 is equal to 20. So 50 times 0.16 is 8. So 8 times W over L of 0 is equal to 20. This means that WRL of 0 is equal to 20 by 8 or 5 by 2 or 2.5. So therefore we choose WRL of 0. We know that the easiest choice is to choose a 0.5 micron length for M0 because as of now there is no CMRR spec, and the size of the width is now simply 2.5 times 0.5, which is 1.25 micrometers. So now we have now selected the sizes of these transistors. We have selected the sizes of M0, we have selected the sizes of M1 and M2, and now we need to decide the size of M3 and M4. As we will go back to the spec, we will find that there is one more spec that we have not used, which is the output swing specification that will set the size of M3 and M4. So the minimum output swing is 3 volts peak to peak. So let us assume that this swing is equally distributed on the upper side and the lower side. So let us depict it on this particular picture. We will assume that feedback is used to set V0 to be equal to VDD by 2 or 2.5 volts, which is a fairly good estimate, which is a fairly good place to bias the op-amp. Now on top of this 2.5 volts, we now want a 3 volt peak to peak swing, which means the amplitude is 1.5 volts. And at that point, the transistors on either side should just touch the triode region. This tells us that the VD sat of M4 should be equal to 2.5 minus 1.5 equals 1 volt. This now sets the size of M4. Let us now calculate that. So VD sat 4 is simply 2ID4 over mu and C aux WRL4, and since this is equal to 1, we will square both sides and point out that 2 into ID4 is 5 microamps should be equal to mu and C aux, which is 100 microamp per volt squared times WRL of 4. Now as you can see, WRL of 4 needs to be 0.1, but clearly a width of which is smaller than the length is normally not possible, and therefore we will say that W4 is equal to L4 is equal to 0.5 micrometers. So we will say that this value is 1, in which case VD sat is even lower than required. Finally, we have to ensure, for this to be correct, we have to ensure that if V0 needs to be easily biased at 2.5, VCM in needs to be biased appropriately. So that the output can be set to 2.5 volts. And as we have seen, the maximum output voltage, just like we said that the minimum output voltage is 1 volt, the maximum output voltage is 4 volts, in which case the common mode at the input needs to be set such that the sum of these two voltages with the other polarity, of course, because we have a PMos OpAmp. So the sum of these two voltages at the edge of triode regions should be equal to 1 volt. Let us quickly check if that is true. The final condition is that VD sat of M2 plus VD sat of M0 should be equal to 1 volt. Let us check if this is true. VD sat 2. So we have seen that VSG1 is 1.1 volts. So which is the same as VSG2. And VSD sat 0 is here, which is 0.4 volts. By design, clearly VD sat 2 plus VD sat 0 is 0.5 volts, which is less than 1 volts. Swing limit possible is achieved. Please note, for this final swing limit condition that we have applied at the end, I have assumed that the gain of the amplifier is so large that for the triode condition I can neglect the gains, neglect the swings at the gate. So please note this. For a hand calculation, this is often perfectly fine as long as the gain of the amplifier is very large. In this case, our DC gain is 500, so therefore we have no problems with neglecting the swings at M1 and M2 gates.